So we want to welcome Daniel Neumaier, who received his PhD degrees in 2009 from the University of Regensburg. He was head of the Graphene group at AMO, a research foundry located in Aachen, Germany, from 2009 till 2020. Since 2020, he's full professor for electrical engineering at the University of Wuppertal and scientific advisor at AMO. Daniel Neumaier has managed several research projects on graphene and related 2D materials. He is currently leading work package 4 in the 2D experimental pilot line project Modules for Industry, and he coordinates the EU FET Open project Original. So Daniel, let's not hesitate too long, so the floor is yours.
Thanks a lot for that very kind introduction, and welcome to everybody. Good afternoon. In this first webinar of the graphene series, I will give a basic introduction to graphene. So what is graphene, and afterwards, what can we do with graphene? So different applications in electronics, photonics, and sensor devices, focusing on those which can be realized by the next multi-project wafer run offered by the 2D EPL project. And in the next webinar, Gordon Rinke will give you details on the MPW run after hearing all those details here on the application. So graphene, to make the long story short, okay. Now it switches. It's simply a carbon allotrope. And with carbon, we have a couple of allotropes, which means crystalline forms where carbon exists. Well, the well-known forms are, of course, diamond, the 3D form of carbon, and as well as graphite, known for centuries. And in the 80s, a new form of carbon or new carbon allotrope popped up, fullerenes or buckyballs, C60s, which is zero-dimensional, or which, to say it in other words, is a small molecule made out of carbon only. In the 90s, the 1D form of carbon was discovered, carbon nanotubes, and beginning of 2000, mid of the 2000s, graphene, which can be seen as a single sheet of carbon or a single sheet out of a crystal, graphite crystal, appeared on the floor, and that discovery was honored with a Nobel Prize for the two scientists, Geim and Novoselov, in 2010. So what is graphene? It's simply a two-dimensional arrangement of carbon atoms or a single slice of graphite crystal, so carbon organized in a hexagonal arrangement. Graphene was the first 2D material to be investigated in more detail, but it's not the only 2D material. And with the rise of graphene, several other 2D material popped up, and nowadays there are more than 100 2D material actually produced, and theoretically predicted even much more, well above 1,000. And 2D materials, they can cover all kind of material classes. So we have graphene. That's what I will go into detail in the next slide. It's a thin metal without a band gap, but we also have insulators like hexagonal boronitride. We have semiconductors like molybdenum sulfide, tungsten deselenide, so N-type, and also P-type semiconductors. We have half metals. We have metals like vanadium disulfide, and we also have superconductors. So we can cover all kind of electronic properties using 2D material. But now let's come back to graphene, because the first MPW run offered by the 2D EPL project focuses on graphene. So why graphene, and what are the basic properties of graphene? Well, first of all, graphene is a conducting material. I already showed it on the slide before. It's some kind, or it can be considered as a semi or half metal, because it has zero band gap. But the more important property is its high carrier mobility, and values up to 200,000 square centimeter per volt seconds have been observed in graphene at room temperature. Of course, it depends on the quality and the way you treat graphene, but those numbers, they are really exceptional. So for comparison, silicon room temperature mobility for electrons is something like 1,400 square centimeters, so you're a factor of 100 to 200 above silicon, and it's also the highest value of any material measured at room temperature. That's quite outstanding, and that was the beginning of the hype around graphene and intense investigations in the last 15, 16, 17 years. It's also ultimately thin. It's only 1 carbon atom thick, which corresponds to around about 0.3 nanometer, and has a pretty low density of states. That's for application not so relevant at first view, but it becomes relevant if you go into the detail of the device operation. It's optical transparent, flexible and strong, chemically inert and biocompatible. For the applications which we cover by the MPW run, the properties which are important for us are high carrier mobility, because that translates into a very high transconductance of the transistor. It's thinness. Well, the thinness is a key advantage for sensor devices. I will show you on the later slides, because it means in the end that the crystal consists only of surface. And therefore, you get a very high sensitivity to anything which attaches to the surface, as you don't have any bulk material which is not affected by surface chemistry. And for the sensing part, of course, being chemically inert and biocompatible is a very strong asset. So these are the key quantities which we will require in the end for the applications covered by the MPW run. Now, which kind of different applications do we have for 2D materials in general and graphene specifically? So this slide gives you a brief overview on the possible applications of graphene, so illustrated in orange, and also semiconducting 2D materials like molybdenum sulfide. TMDC stands for transition metal dechalcogenides. Molybdenum sulfide is a good representative of those. And as you can imagine, a semiconductor has a different application scenario as a half metal. And what do we have? Of course, RF electronics, because of the high charge carrier mobility, logic devices for the semiconductors, especially for ultra-scaled logic devices where you need a very thin body, sensors, flexible electronics, membranes, of course, and also as composite material in the coatings, shielding, corrosion protection, and in the packaging. The applications which are relevant right now in this talk, or which I will cover, are the applications in the upper right circle related to sensors. So gas sensors, light sensors, chemical sensors, and magnetic field sensors. Now, brief outline of the talk. What can you expect in the later slides? So first, I will go through the basic device, which we will offer in the first MPW run. This is a graphene-based field effect transistor. And this one can be used for gas biological sensors, so I will introduce that application scenario, as a photodetector, and as a magnetic field sensor. That will cover approximately the next 20 minutes, and the remaining time I will spend on the basic manufacturing process for graphene-based field effector transistors on wafer scale. So a graphene-based field effect transistor does not look much different compared to any other thin film transistor. So it looks different, of course, to silicon-based transistors, but if you compare it to thin film transistors like indium gallium zinc oxide or organic transistors, it looks pretty similar. So you have a substrate. The substrate can be nearly anything. So it can be a rigid silicon wafer, a silicon CMOS wafer, or some foil-based substrate like a polyimide foil. Then you have often a gate electrode. In this case, it's a local backgate electrode made out of metal. Then a dielectric on top, the gate dielectric. It contains the graphene layer, and the graphene is contacted source and drain with some metallic contacts. And on top you have some encapsulation layer, which in case you need to open it can of course be opened. So these are the basic components of a graphene-based field effect transistor. And how does the key parameters look like? And here comes in the different compared to other field effect transistors. So if you have a look to the transfer characteristic means you sweep the gate voltage and measure the drain current as a constant drain voltage. you see some kind of ambipolar behavior. You have a hole conducting branch and you have an electron conducting branch. But what you don't see is that the current drops to zero as in a normal field effect transistor. And that is because we don't have a band gap. And the contacts work equally for holes and electrons. So we have contacts which can inject both electrons and holes. And that's essentially because graphene doesn't form any Schottky barrier to any metal. And also there's no threshold voltage and also no threshold swing. So for logic operation, the transistor is pretty useless as you cannot turn it off. What we have instead is some kind of charge neutrality point that's indicated here. It's a minimum point of conductance, often called Dirac point. And here the total numbers of carriers is minimal, and usually also the electrons and holes equal each other. And what we also see is that the slope, transconductance it's called, on both sides, it's pretty similar. So we have similar mobility for the electrons and the holes. Now, if we look to the other key characteristic of that transistor, which is the output characteristic. So here you measure the drain current as a function of the drain source voltage while keeping the gate voltage constant. What you see if you have very thick gate dielectric is strictly linear behavior. So here in that case, at small voltages, you can imagine that. That's because we have no band gap and therefore also no pinch off. If you go to thinner dielectric, it changes slightly to an S-shaped behavior. Here you can see that nice S-shaped behavior. And that's essentially because you have a local modulation of the charge carrier concentration. So you see some kind of onset of a pinch off. And if not the other kind of carrier type would pop into the transport, you would see a pinch off. But as we can inject both electrons and holes, and they can pretty well recombine inside the channel, we see not a pinch off, but that rising up. And therefore, the intrinsic voltage gain is also not too high. It's typically well below 10. So in the end, that means, or the question comes, of course, up, why shall we use graphene field effect transistor for any application? Because for usual transistor application, logic operation, signal amplification, that sounds like a pretty useless device as it does not turn off and it also does not saturate. But it is really interesting for sensing application. Why? It has an extremely high transconductance, and that comes from the high carrier mobility. That means that a slight change in the carrier concentration significantly changes the current through the device. And it has a very high volume to surface ratio and also no dead layer at the surface, which means that anything which you put onto the surface has an immediate impact on the transport properties in the channel. So in the end, you have a material or device which is an excellent transducer for changes at the interface, as either top or bottom interface, depending on which interface is exposed to the environment. And that's ideal for sensor application. So let's have a look how such a sensor could look like. And let's start with the most simple concept. So you have a graphene field effect transistor, it's encapsulated, and in some areas you open up the encapsulation, not illustrated here, in order to expose it to the environment. So the doping level or carrier concentration in the graphene channel is then or depends on the molecules which interact from on the top with the graphene due to charge transfer. And that will change the current through the graphene field effect transistor if it's biased as a fixed bias and gate voltage. And therefore the total current changes in the transistor. And this is the sensor signal which you can read out in order to detect the quantity which you want to sense. And now you have two approaches which you can go. The first approach is you can just keep the graphene channel naked, so it does not, you don't cover it with anything, which means you have a very sensitive sensor, but nearly everything which will be exposed to the graphene channel will affect the conductance, and therefore you don't have any selectivity. And the other approach is to do some functionalization of the sensor surface, and that functionalization provides a selectivity, because to the functionalization, if you do it in a right way, only specific quantities can attach, And this will lead then to a charge transfer to the graphene only through specific quantities at the top interface. And therefore you get not only a high sensitivity, but also a good selectivity. And I will show two examples from literature in the last couple of years for both two approaches in the coming slides. So first one, naked graphene. You have a graphene encapsulated and you remove the encapsulation. And then you can expose it to different environments. So what has been done here, it was exposed to ethanol atmosphere and also to a change in the humidity. And as you can see, the resistance through the device when exposed to ethanol changes immediately on not rather fast, but a sufficiently fast timescale, and it can be reset by removing the molecules from the surface. Here in case it was 280 nanometer UV light. But as you see with red line, if you change the humidity, you also get some signal, so some resistance change. Here it's more reversal, but in the end it means you have a very sensitive sensor device, but it is not useful if you don't know exactly which kind of environment you have. So you have a pretty poor selectivity between the different gases. So it's only a useful approach if you know which environment you have. So in a controlled environment, and you also know which gases you want to sense. For instance, if you want to sense the ethanol concentration in a nitrogen atmosphere where you don't have any moisture and any other gases, that's a pretty good approach. But usually in application scenarios, that is not the case. So you need to go for some functionalization. And here, the functionalization in this example, that's for NH3 detection, has been performed chemically in a non-covalent way. So the top surface of graphene has been covered by a rather complex molecule. So I'm not really a chemist, so I cannot tell you any details of that molecule, but that molecule provides you some selectivity, as only NH3 is able to attach to the molecule, and therefore only NH3 will provide some charge transfer to the graphene, affecting the conductivity of the graphene. And here that has been tested for NH3 in different environments, here in a controlled environment and to the middle in both in normal air and in H2, and you see that it's a pretty sensitive sensor towards NH3. And if you expose, in contrast, other gases to the graphene, you see that only NH3 is the one which changes the conductivity of graphene, while all the other gases remain or leave the conductivity of graphene unchanged. So you can remove that disadvantage of graphene, that it's sensitive to everything, simply by doing a dedicated surface functionalization, adding some selectivity or some clear selectivity to the sensor. This can not only be done to gases, but nearly for everything. So for biosensors or biological sensors, you can functionalize the graphene surface by antibodies, so that cells, microorganisms can attach with different enzymes for ions and molecules, and also for nucleic acid detection, specific functionalization can be performed. More details can be found here in that review paper if you are more interested in the specific state of the art in that field and which kind of detection is possible using those graphene-based sensors. Now, a quite similar application scenario for graphene field effect transistors is a sensor for light. Well, graphene absorbs light, but only slightly. It is nearly transparent, so it, under normal incidence, typically absorbs 2 to 3% of the incident light. So in order to make a useful photodetector, you need also to do some functionalization. And one approach which is possible with the devices offered in the first MPW run is the functionalization by quantum dots. So you put quantum dots of a graphene field effect transistor. This is the functionalization layer. And these quantum dots, how does it work, the device? They absorb the light. Light comes from the top. All the light is absorbed in the quantum dots. So you generate an electron-hole pair inside the quantum dots. Depending on the quantum dots, well, of course, the chemical the work function of the quantum dots is changed. And that means you have some charge transfer from the quantum dots to the graphene because of the changed work function in the quantum dots due to the light exposure. In that case, the electrons remain in the quantum dots, the holes are transferred to the graphene, and this leads to a change in the conductance in the graphene channel, and therefore you have a readout signal which depends on the intensity of light exposed on the quantum dots. The response time of that photodetector depends, of course, on the electron-hole recombination in the quantum dots. That's limiting factor. So usually you have some hundreds of microseconds, which is sufficient for imaging. And also the absorption spectrum depends on the absorption spectrum of the quantum dots, which adds a new degree of freedom. The key advantage here is that you have a pretty good transducer, and that provides you a very high internal gain. And therefore, responsivities of the order 10 to the power of 7 amps per watt, 10 to the power of 8 amps per watt have been achieved with this kind of geometry. As said before, the spectral sensitivity or the color of the light which you absorb depends on the quantum dot you put on top. And in the quantum dot, that depends on either the size of the quantum dots. The smaller, the more to the blue wavelengths, the absorption spectrum shifts, but it also depends on the chemical composition of the quantum dots. So using lead sulfide quantum dots, you can, for instance, absorb pretty well infrared light around 900 nanometer near infrared or more to the mid infrared around 1500 nanometer using larger lead sulfide quantum dots. And therefore you have a pretty simple way to construct a infrared photodetector using graphene transistors and also quantum dots without the need for the more expensive 3.5 semiconductors. And now, as we are flexible on the substrate, these kind of photodetectors can be integrated in a 3D arrangement on a silicon CMOS readout circuitry. This has been done by a group at ICFO in Spain in 2017. They used commercial available CMOS readout circuitry in an array, fabricated an array of graphene transistors with quantum dot functionalization on top, and therefore were able to realize an infrared camera using silicon CMOS and graphene in a 3D heterointegration scheme, which is a quite interesting way in order to realize cost-efficient and powerful infrared imaging systems. Now, the final application which I want to mention with graphene-based field effect transistors are Hall sensors. Hall sensors are sensors for magnetic field. And they are probably among the most fabricated type of sensors because in all of our mobile devices, we have magnetic field sensors for positioning. We have them in automotive applications for sensing the position of a steering wheel, the seat belt, and so on. So approximately several billions of Hall sensors are manufactured each year. And the key operation principle of a Hall sensor, most of you will know that, is that you have some kind of Hall cross. You have 4 electrodes. Current is flowing here from the left to the right. You measure the voltage on top and from the bottom and apply a magnetic field perpendicular to the plane. And the voltage which you measure perpendicular to the current and to the magnetic field depends linearly on the magnetic field. And the device becomes sensitive if 2 parameters are fulfilled. First of all, it becomes more sensitive the higher the carrier mobility is, and it becomes more sensitive the lower the sheet carrier concentration is. That means you need a high mobility material. Graphene is perfectly suited for that, and a very thin material because that allows you to have a very low sheet carrier density. And therefore, graphene is probably the best choice available in both respects. And as you can see in the current normalized and voltage normalized sensitivity, the values which have been obtained for graphene are a factor of 50 or 30 higher compared to silicon, which is state-of-the-art in Hall sensors, and also higher compared to the best gallium arsenide and indium antimonide based Hall sensor, essentially because you have a very thin material with extremely high carrier mobility. Now, let me quickly summarize the part on the applications before coming to the manufacturing. So important considerations if you have a graphene field effect transistors, which you need to take into account, is that your top surface needs to be as clean as possible. Also, you need to have very high carrier mobility in order to get a high current change, and that can only be achieved by having a clean surface and low defect density. Low contact resistance, this is something obvious in order to get a good sensor signal. Low noise level, especially 1/f noise as the dominating noise at low frequencies. This can be achieved by very good oxides or by low defect density at the oxide graphene interface. You should avoid parasitic drift, so stable operation, and the graphene transistors should have well-defined parameters, especially for the mobility and the doping level here, CNP, charge neutrality point. And all of this means the better your process technology is developed, the better it is for the final application, because then you can rely on the parameters and you get the best available performance. Now let's come to the last part, to the smaller part of that presentation, the possible integration scheme. And here as an example, I illustrate the integration on silicon CMOS in a very nice PowerPoint schematic, or very easy PowerPoint schematic. So you start with a silicon CMOS chip. You have the front end of line with the silicon CMOS transistors. You have already processed some kind of back end of line with the copper interconnects. Then you can transfer the graphene layer. You can do the patterning of the graphene, encapsulate it, edge vias, and contact the graphene. Up to this stage, these process steps would be sufficient for graphene-based Hall sensors. If you, in the next step, open up the graphene channel and functionalize it, you can integrate graphene-based sensors easily on a silicon CMOS platform. I say easily because in this PowerPoint schematic, it looks really easy, but in the end, it's quite tricky to control all these parameters or all these process steps. To mention one of the key difficulties when it comes to processing graphene, if you compare it to silicon, is to keep the surface clean. So everything you put on top of graphene might lead to some residuals, and in contrast to other semiconductors, cleaning those residuals is not possible. In silicon, if you want to strip it from the photoresist, you just expose it to oxygen plasma. That removes everything from the photoresist and you get a very nice silicon interface back. If you do that with graphene, well, you can imagine that carbon atoms and oxygen plasma are pretty good friends, so you will also easily remove all the graphene layer, especially keeping in mind that it's only one atom thick. So most of the cleaning methods which you have from silicon technology are not available for processing graphene, and therefore you need to find different approaches in order to not contaminate at all the graphene from the very beginning. And these are the key tricks which need to be developed in order to achieve a very powerful sensor technology platform. So to sum up the essential steps which we have a growth of graphene, which is performed on a separate substrate. We have the preparation of the target substrate, then it needs to be transferred to the target substrate, encapsulated, patterned, and contacted. And the essential steps are the three marked here. So preparation of the target substrate, that defines the lower interface. Transfer to the target substrate, the handling often leads to some contamination, and the encapsulation. And these decisive steps, or these are the decisive steps because they defined the surface interface on the top and at the bottom, and also the level of contamination which the graphene layer receives during the processing. Now let's start, or let's give a basic introduction to the growth of graphene, because this is something which is most relevant. And the initial growth of graphene was the micromechanical exfoliation, also known as the Scotch tape technique, which was applied by the Nobel laureates Geim and Novoselov in the early beginning. So they used graphite flakes, and with Scotch tape, they made graphite thinner and thinner until they reached a single layer. And here on that optical image, you see graphene. The contrast is some 4-3% to the substrate, and it's essentially a monolayer single crystalline graphene with the size of 0.03 millimeter, so that corresponds to 30 micrometer. And that's a typical size of a graphene flake, which you get with the Scotch tape technique. For application, that's of course a dead end, but for basic science, that is or was one of the keys for the success of graphene, because it allows any researcher on the world to easily exfoliate graphene in their lab and to make graphene-based devices and do experiments on graphene. But as said, while this is good for basic science, it's not good for application. Therefore, in the last 15 years, vapor scale methods have been developed. And the most prominent one, which will be also used for the MPW run, is the chemical vapor deposition growth of graphene. Here, this is a commercial tool provided from a company in Aachen, Extron. They have it from 2-inch wafers up to 12-inch wafers, so they cover all wafer sizes. And with this tool, you can deposit a monolayer of graphene. Most often it's done on copper surface, like here in the image, on rather large scale. And it's clearly, it's really a monolayer, polycrystalline with crystallite sizes of several tens of micrometer. And the right SEM image, it shows you the copper film on a silicon surface to the right. So here you see the step, and the copper has been removed by wet chemical etching in some parts for illustration purpose. And here what you see is a carpet, graphene carpet, hanging over the edge from the copper to the substrate. And that's quite impressive that this graphene film is not only visible clearly in the SEM, but it's also so stable that it survives also the under etching of the copper film. The transfer process, you don't want to have it on a copper, but you want to have it in any other wafer. It's also has also been well developed in the last couple of years, and that's usually based on supporting foils. So you have graphene on copper. Here it's a roll-to-roll process, but it can also be batch-to-batch. You put in a polymer foil on top. You remove either the copper or you delaminate the graphene from the copper by ripping it off or intercalating it chemically. Then you end up with graphene on a polymer support foil, which you can then laminate on your target wafer or on your target foil. And that allows you either to cover 12-inch wafers with graphene or meters of graphene using that roll-to-roll continuous processing. And then I'm already at the pretty end of the presentation. I will introduce quickly the first or the baseline process, which we have in the multi-project wafer run number 1. And this is essentially a process for backgated graphene transistors, as I illustrated it before. So we have a silicon oxide substrate, then backgate electrodes, dielectric, graphene transfer, graphene contacting. Contacting is done from the bottom and from the top with sandwich contacts, and then some encapsulation layer and opening of the encapsulation layer at dedicated places, which of course can be designed by the customers, and the whole processing is performed on a 200mm platform, and that's an optical image of a graphene wafer which has been processed approximately 1.5 years ago in the clean room at AMO. And the details of that MPW run, which will be offered this year or is already open, the call for designs will be given in the next webinar by my colleague Gordon Rink on May 12th. At the same time, also a Thursday, if I remember correctly, and he will show you the key specification and the key requirements, including the design rules for that MPW run. In the webinar afterwards, my colleague Mika Soikeli from VTT, He will show the next step, which is towards the integration of those sensors, not only on silicon oxide, but on an active CMOS layer, so that you can combine CMOS electronics for the readout with the Graphene sensors. And also on the website of the Graphene Flagship, you can find more details about the MPW runs and also about the flagship in general. And with that, let me thank you for your attention.